In this next section of lecture videos, we're going to focus on titrations. And we'll start with the titration calculations that we've already seen in past classes and build up to weak acid titrations. Um, and we'll be looking at pH curves and indicators and all of that fun stuff. So let's dive in. So as a refresher, titration, or can be a lot of things actually. We're focusing on acid-base titrations, but you can do redox titrations as well. But what we do is a solution of an unknown concentration is typically placed in a burette, and that's our titrant. Anything in our burette will be our titrant. And it's slowly added to a solution that we know the concentration of, our analyte. And we'll slowly add it drop by drop by drop until a complete acid-base reaction has taken place. And by this, I mean that we've actually got a stoichiometric ratio of acid and base reacting together. So it means that the same number of moles of our base have reacted with our acid. So we are at a neutral pH when we hit our equivalence point. Or at least we are if we're doing a strong acid and a strong base. So this is the typical introductory chemistry titration that you do. It is usually a strong base or acid in our burette and a strong acid or base as an analyte in our flask. And we use phenolphthalein, which is an indicator dye that will be totally clear when something is acidic, and then it will become a pale, pale, pale pink, and then a dark pink once it is neutral and then basic. So we can see that equivalence point if it's around pH 7 to 8 for phenolphthalein. The calculations that you've hopefully seen before around this are really a set of stoichiometry calculations, solution stoichiometry. So usually you either know the volume of your solution or its concentration or both. And you can use that information to determine the number of moles of acid and base you have, which can then help you calculate an unknown concentration. So typically we are looking for a unknown concentration of, let's say, an acid. And we know the volume of base that we've added and the volume of acid that we had. So we'll have, let's say, the acid, which is unknown in our beaker, or it's in the type, or actually here, let's say we've got our known base, it's in the beaker, and we know its volume and we know its concentration exactly. And then we'll add our acid slowly until we get that light pink color. We're like, cool, we've neutralized this base. We have a stoichiometric ratio of acid to base. The volume that we're reading from the burette gives us the information about how much we used. And then we can combine the moles of base, well, the information about the moles of base. So these two together get us the moles of base. We can convert that in a mole-to-mole conversion using our coefficients in our balanced equation to get the moles of acid. And then we take that moles of acid and the volume of acid to calculate our actual concentration. As you've seen, a lot of acid-base reactions are involve the transfer of one proton. So a lot of times when we're doing these titrations, we have a 1-to-1 mole ratio for our acid plus our base. An example of this would be sodium hydroxide plus hydrochloric acid forms sodium chloride and water. So I have a 1-to-1 mole ratio here between my sodium hydroxide and my hydrochloric acid. And so we have this equation you may have learned that simplifies things. It looks like the dilution calculation. And that's because it hinges on the fact that the moles of acid and base are the same. Kind of like in a dilution, the moles of whatever solute you have is the same before and after you add water. So we could do this either way. I'm going to walk through a sample calculation now just as a refresher. You can try it first yourself. Here's our example. We're going to look at that hydrochloric acid and sodium hydroxide titration with one another. And we're going to have information about the sodium hydroxide in this one. We know we have 17.3 milliliters of it will be added to get to the titration, or sorry, the equivalence point. And it has a 1.5 molar concentration. Our hydrochloric acid, we don't know the concentration, but we know that we have 25 milliliters. And our goal is to calculate the concentration of the acid. So put a little question mark there. So the way I would approach this, I'll show both ways. Like I always go to the solution stoichiometry way because remembering equations is like extra work to me, but maybe not to you. So what I would do is I would work in liters if I was doing the stoichiometry version. So that 17.3 milliliters will be 0.0173 liters. That 25 milliliters will be 0.025 liters. And I'll start by first figuring out, well, I know stuff about the sodium hydroxide, so I'll figure out what the number of moles I have of that is. So I'll start with that 0.0173 liters. And I am going to convert into moles using my molarity, 1.5 moles per liter. And that's going to give me a value of 0.02595 moles of NaOH. I'm going to convert that now into my moles of HCl. And this is a 1-to-1 reaction. So this is times 1 and divided by 1. Pretty straightforward. So now I know my moles of acid are 0.02595. And then I'm going to use that to calculate the molarity of that HCl. It's going to be the number of moles divided by my total volume. Oh, sorry, that would be of my total solution. I wanted to know what the original acid solution's concentration is. So that means I'm going to use that 25 milliliters of acid that I started with. So that's the 0.025 liters. And that gives me a concentration. If I use just 2 sig figs, it's 1.0, but 1.038 molar, so 1.0. And that's how I figure out the concentration of that acid. I would take a small amount of the acid I was working with for another reaction. I would titrate it to get the exact concentration, and then I would know. I could also do that. So here's one method. So another way to do this is using that C1V1 equals C, or concentration of acid times volume of acid equals concentration of base times volume of base. How about that? So we don't know the concentration of the acid, but we know our volume is 25 milliliters. Since I have units volume on both sides of the equation, I can use any units I want as long as they're the same, whether that's liters or milliliters. So I don't have to do the conversion if I don't want to. I can also do it if I want. And then I have my 1.5 molar times my 17.3 milliliters. If I plug that all in and solve for the concentration of acid, I'm going to get the exact same thing. There we go. And hopefully this is familiar from your first class in the Chem series. If not, hopefully this is a refresher. And so what these titration curves would look like. So let's say we're doing this titration experiment for that strong acid, hydrochloric acid, and that strong base, sodium hydroxide. And let's say we measured the pH along the way. Like every drop, we took a pH reading. It'd be tedious, but let's say we do it. We would get a graph that would look like this one here if I plot the pH versus the volume of my base that I'm adding slowly. So that assumes that base is in the burette and I'm slowly adding more and more and more and more and more. And I'll have, taking the pH of what's in my flask, if that's my acid, I'll have a low pH to start out with, right? So this is the pH of just my acid. And as I add some of this sodium hydroxide, right, more of my acid is neutralized. And I see a very slow change in pH until I get close to my equivalence point. And that equivalence point is when I've added the same amount of base as I have with my acids. We're at a stoichiometric addition of base at this point. So I have the same amount, I have the same moles of acid as I have of base at that equivalence point. And you can see that pH comes up quickly and it's neutral. Now, after that point, every drop of NaOH I add is just adding hydroxide ions to a neutral solution. So it very quickly becomes right here, basic. And so after that equivalence point, my pH will continue to change dramatically until I'm basically just at the pH of the sodium hydroxide solution I'm adding in. And this is what a titration curve will look like. And we can always tell that equivalence point because even if we don't know exactly where it is, if we graph it and we find the same shape every time of this part of the line that has a slope of almost, it's like a 0 or 1, I forget which one. Right in the middle is where our equivalence point would be. And so I can always come in and kind of extend these lines here. And if I look between these right here at exactly 1/2 the height, I'm going to find that equivalence point. And so hopefully this pattern becomes familiar. If we have a polyprotic acid, it's going to look the same but different. If we have a polyprotic acid, it means that there are multiple hydrogen atoms that can react with a base. So the most acidic will react first, and all of those protons will react. And only after they're done completely reacting, that acid-base reaction is completed, will the second acidic hydrogen start to react with the base. And so we're going to see 2 equivalence points when we have a diprotic acid. If we had a triprotic acid, we would see 3 equivalence points. So here's an example of a diprotic acid. It's carbonic acid. And so our first equivalence point right here is coming from the reaction of carbonic acid with water to form bicarbonate. And so it's then the bicarbonate reacting with water that is to form carbonate ion right here. That is the acid-base reaction that's happening at the second equivalence point. And so if you see multiple these kind of jumps or plateaus in a titration curve, it just means that you have that many acidic protons that were lost in the acid-base reaction, or that tells you if it's what kind of polyprotic acid it really is.